of the sessions we have had so far. And we want to do this coffee chats to create a virtual platform for knowledge exchange and discussion around the latest scientific and technological developments in sustainable lithium-ion battery manufacturing. My name is Stina Starboy. I'm host of today, and I'm part of the coordination team in NoVOC, which is arranging these coffee chat sessions. For today, the agenda for today is welcome and an intro, and then we will have our keynote, Iratxe, and then we will for 25 minutes, and then we will have 10 minutes breakout sessions for informal exchange, and then we will have 50 minutes of questions and answers, and then we will close the webinar. And this webinar will be recorded, and that's the presentation part. And please change your name to first name and where you come from, and turn your camera on during breakout and question and answer sessions, and mute yourself when you are not speaking, and post your questions in question and answer in chat during the presentation, and or raise your virtual hand during the question and answer session. Today's keynote is Iratxe de Meatza. She's project manager and team leader for advanced lithium ions at Cidetec Energy Storage. And she is born in 1977 in Bilbao, in Spain, and studied chemistry with a postgraduate focus on inorganic materials, and PhD at University of Basque Country. She has focused on lithium-ion batteries, electrode formulations and processing optimization, full cell harmonization, electrochemical characterization, cell prototyping since 2004. And she has participated in more than 20 European projects on batteries, and is co-author of more than 45 scientific papers, and have one patent on aqueous cathode processing. So I leave your hands to Iratxe, which will present the advancements in aqueous cathode fabrication. Thank you.
Yes, thank you. Thank you, Stina. So I will start sharing. Hopefully this should work properly for everyone to be seeing some slides in full screen. So
I can see them.
for
Thank
this,
you.
Yeah. Is it okay?
Yeah, please continue.
Yeah. Okay. So as Stina has mentioned, to provide in this less than half an hour, I could speak for too long, and so please stop me when necessary for the 25 minutes, because I have quite a lot of information on the slides, but it's just to put forward the case of waterborne cathode manufacturing, where is mostly the challenge to work with water-based slurries for wet electrode coating manufacturing processes, and particularly on going to the upscaling when you start to observe more issues, since the anode manufacturing is already industrial standard to work with waterborne slurries. So if anyone has curiosity on that, containing silicon, there are some particularities when introducing silicon in carbon-based anodes and on water-based processing, but the major challenge is on the cathode side. So mainly working with these NMC type oxides. There is also high voltage spinel as one alternative cathode that can also be processed in water, where typically all the manufacturing is done using NMP as the solvent. So this comes from quite a nice review on waterborne cathode processing and different binder systems that can be used already from several years ago from the group at HIU, from Dominic Bresser as first author in this case. So on cathode waterborne slurry preparation, mixing, and then on the coating process compared to the standard process in which the polymer binder, the standard is PVDF, which is soluble in NMP, but this NMP, N-methylpyrrolidone, is a volatile organic compound that, as in NoVOC, we want to get rid of this because it has toxicity issues. Also, in that sense, and not only for the operators working on a coating line for electrode manufacturing, that of course you will have all your protection measures, but since we are then evaporating after casting this slurry, we are evaporating the solvent to get to the dry electrode that then goes into the cell. NMP then requires a whole, quite a costly operational system of to collect and recover with filters this NMP because it cannot get emitted onto the atmosphere. That will cause, of course, some higher CO2 footprint, but also its toxicity then cannot be released onto the atmosphere. And this issue is resolved, or is not an issue anymore when using water as the solvent and dispersion media of the electrode component. As we can see in the scheme, we have the active material, the main component, but also a series of conducting additives, mostly based on carbon, and the polymer, the binder that brings everything together and keeps the mechanical stability and adhesion to the metallic substrate, aluminum in the case of cathodes, the foil, that then gets stuck or bound when assembling the cells. So in this nice scheme, you see the advantages mostly highlighted of using water as this dissolving, dispersing media instead of NMP. But to be able to transfer this water-based processing on cathode electrode manufacturing, of course, we are trying to replace the PVDF also, so getting rid of fluorinated compounds. Also, the PVDF can be a source of PFAS, of these perfluoroalkyl compounds that will be more and more regulated in the European Union, but it's also the fluorinated compounds that we want to get rid of. The fluor is important in batteries, also the lithium salt of the electrolyte component. But in the case of the polymer binder, the fluorinated polymers are also highly stable to the oxidation, the cathodic voltages on which the cathode operates. So we also have to find a suitable fluorine-free polymer binder that can be stable dispersion in water or dissolve in water. Main issues then is that since we are working with water as the solving media, then we will also have to be more careful of removing any residual moisture, residual water trapped in the porous electrode on the drying step, but particularly on the mixing steps are the main problems. It's more difficult to avoid agglomeration of some of the components together, so then the electrodes are not as homogeneous, the dispersion of the electrode components are not as homogeneous as with the standard PDF in NMP. And the two main issues are related to the behavior of particularly these nickel and particularly high nickel-based oxides, the cathode active materials towards the exposure to water. So then in contact with water, there is more tendency, particularly of the NMC cathode active materials, to react with water and leach the transition metal ions, so the nickel, manganese, cobalt, and also to dissolve and leach and lose lithium, the lithium ion too, from the cathode active material particle, and issues related with the then high basicity, high pH of these suspension, these slurries in water, is that it affects and corrodes and passivates the aluminum foil, the current collector in which we are coating to manufacture these electrodes, and as well the wettability of these water-based inks or slurries in this aluminum surface. But the main issue is particularly that since the pH tends to be more basic than when it's the pH is higher than 9, then we start observing this leaching from the active material, and as well as leading to the corrosion of the aluminum current collector, that then in that case also leads to gassing, because it evolves when reacting the aluminum, it creates a passive aluminum oxide on the surface, which then reduces the performance of the overall electrode, but it also generates hydrogen that can then, of course, evaporates, but this is also related to the corrosion issue. With other type of cathodes, in my experience, we have been working on water-based cathode slurries and processing since 2012 or roundabouts. We published in 2016 these results with LFP cathode active material, which is a phosphate, so not an oxide, so it's more stable and less sensitive to water. It's also carbon coated, so that helps on this stability towards water. So it was kind of like the starting point and less challenging in terms of all these issues that I have mentioned that are mostly related to the layer oxides in terms of the cathode. But as I was mentioning, related to the drying step at the end, since there is water-based slurry composition, some of these components will be more hydrophilic than the standard PDF in NMP processing. We also have to be more conscious of the final drying step to be below a certain threshold in terms of residual water ppms remaining into the pores of the electrodes possessing water, that if this is too high, then this water can be released within the cell during operation and react with electrolyte, generate HF, and of course a reduction of the performance of the battery that has been manufactured with this kind of electrodes. But let's say the LFP cathode active material can be processed, and already some time ago we work on this, and it's demonstrated. Then going towards the NMC cathode active materials is where the challenges start to get more difficult. In the NMC 111, when you have 1/3 of each of the transition metals, nickel, manganese, and cobalt, the pH, if the active material particle is not particularly surface treated, the pH can be higher than 10, but not as high as with the higher nickel content oxides. So there was this work in which we also collaborated at the time of an FP6 European project called Green Lion that led to a patent, a German patent deposited by the University of Münster, of using the phosphoric acid as pH buffer to regulate this pH and keep it at around 9 and not higher than that to avoid the aluminum corrosion. The NMC 111 active material is not so susceptible towards the leaching, but this phosphoric acid was introduced at that time, in fact, as this pH buffer and regulator. Still here, at the time, the amount of active material was below 90%, which is low for what we are dealing with at the moment, that it's at least 94 or even higher, 95, 96% of the active material to increase the energy density. So a couple of references here, and I will go on to providing a bit more of information on one of these waterborne binders with example of NMC 622. In this case, it was still a PVDF waterborne latex, but still the PVDF, so this fluorinated polymer that I was mentioning, and using the phosphoric acid as a pH buffer. The PVDF latex was from Arkema as a reference. There is no gelation with the addition of PVDF, of the phosphoric acid, that in some NMC systems can be an issue. So in the rheology, it's always important to check the rheological properties, and not only the pH, also to be able to say that these waterborne slurries can be upscaled and processed. So this is the kind of rheological behavior that we would want. Also, to go into upscaling, manufacturing, and expected production, the higher the solid content, the better, because then you have lower solvent to evaporate, so less energy consumption on the drying step after the coating line, but there is always a limit. If you go too high on the solid content, then the slurries start to be less stable or tend to agglomerate, and you will have more defects. Without the pH regulator, for instance, it's more evident the cracking and bubble formation. In fact, in this case, in this picture that I'm pointing out here with the cursor, there was a bubbling due to hydrogen evolution, due to corrosion of the aluminum, and that then was leading to cracking during the drying step. So starting at the lab scale on these 40 grams of solid slurries, then the main challenge goes when you go from these 50 grams, that can be something like 100 milliliter slurry volume, going to coating lines, as we see in this. In this picture, it's at least 1 liter slurries to be able to coat in this continuous line of several meters length. So I will show some videos here just to for everyone to illustrate this kind of upscaling scale. Then when you go to industrial scale at a battery cell manufacturer producing their electrodes, then instead of these, which is more like a 15 liter slurry, you can go even to 100, 200 liters per batch. So after having this with these kind of planetary mixers to mix all the components and prepare the slurry, this is transferred to a coating line. Here, so that way. This is at our old facilities. We moved recently at Cidetec to a new building, so we have to prepare new videos. Also, we have additional coating lines at the moment. This goes with a knife coating head. This will be the drying zones by convection ovens, and those tubes were towards the recovery system when you work with an MP. On the solvent that gets evaporated. That is not necessary when working with water. And this will be the calendering, which is kind of like the final step after coating, roll to roll, and drying. You go to this calendering, which are two rolls that compress the coated layer to densify it to the optimum density for the design cell performance, either to maximize the energy density, compacting as much as possible without losing the power rate that was required, or to the design of the cell and the optimum depending on the active material and the formulation, of course. So, for instance, in this example, it is going at least to 1 liter slurries, so around 50% of solid content, or 57, with this PVDF latex, so stable suspension in water, still of the PVDF. No changes between the pilot plant, this larger slurry, and the lab scale. That's something that is better to confirm every time on the different upscaling steps. This will be the shear thickening behavior that we will look for. For water-based slurry, sometimes it's more difficult to get this nice and continuous slope. As we are seeing here, one of the advantages of the water-based slurry is that the drying temperatures to evaporate the water are lower than the temperatures used for the same system with the standard NMP, so that will lead to also lower energy consumption on this drying step and lower environmental footprint to those that work on life cycle assessment and CO2 footprint calculations. When we went directly with this first upscaling that was working well with the adjustments at lab scale, on the coating line, we were observing this huge issue of the lamination. You see here it's speeding off the electrode at the end of the drying. Even when going at a slow speed to give more time for the drying step. So to solve these issues, which were related to this lower adhesion to the carbon collector, was solved, or one of the ways to solve this with water-based cathode slurries and towards manufacturing is to use carbon-coated or graphitized aluminum current collector foils. So then this possible still corrosion issue at this larger scale is reduced due to having this quite thin carbon coat or graphite layer protecting the surface of the aluminum and also helping on the adhesion of this electrode formulation towards this graphitized layer. So in this case is what we would expect, the micrographs of a cross-section and the surface of a well defined final electrode produced. At this point, the loading for this particular electrode was 3 milliampere per square centimeter, so slightly below 20 milligrams per square centimeter. When trying to improve energy density, going to even higher or higher and higher loadings in terms of aerial capacity, this also leads to thicker electrodes. So all the drying steps, particularly speeds on the coating line and temperatures have to be adjusted, particularly for each of the cases. And then on the drying step that I was mentioning, also at which temperature is post-dry to find the threshold and to reach at least below 500 ppm of residual water that are measured by Carl Fisher, to be able then to go confidently into assembling well-performing cells with these waterborne electrodes. So I will not stop on that point, but just to show that, in fact, then on cycle life of this, which was done in full coin cells at the time, you can also find the article, the scientific paper here, the reference. It's the capacity of retention is better for these processed electrodes, and also there is not additional polarization as we see in the course here, which is also one of the major points when looking at NMC cathode electrodes processing in water. I want to then also provide you some further developments with fluorine-free polymer, which is again a latex, so it's a stable suspension in water, but based on acrylates, another family of polymers and non-fluorinated, in which we have gone further to increase also the cathode active material percentage, and this NMC622 is not particularly developed for water-based slurries, so it's the use of the phosphoric acid, adjusting the amount of this phosphoric acid for the particular NMC, and also adjusting the whole final pH of the final composition and the particular polymer binder that is being used. CMC is always or typically always used also as a stabilizer and as a co-binder in this waterborne processing. So I will not stop on the details here. Also to show mixing steps, go into 10-liter mixer. In this case, a whole matrix of drying conditions. In this case, in another of the coating lines that we have at Cidetec, which has a longer, more drying zones, and also infrared drying area at the beginning. The others are air nozzles, so a different type of drying that you can find in coating lines from conventional ovens too. Even when you think that at the end of the line the electrode is dry, as we are seeing here, we have found that you can find this kind of aluminum oxide deposits on the bound electrodes, particularly when these supposedly dry coated layer is in contact with bare aluminum. The drying was continuing over time, in even when packed or stored into dry room. There was still water that was being dried out of the layer and reacting with the aluminum and creating this passivation and these aluminum oxide deposits, which is not nice. So what it's important, or what we have found, is that it's necessary to reach at least below 5% of residual or relative humidity that you can measure with some simple sensors in the electrodes at the end of the drying before going to the post-drying step, to avoid having these further reactions while the electrode is being post-dried. And as you see here, also all the drying and this porosity that is arising in the morphology of the coated layer, then depending on how you calendar, the porosity and tortuosity of these water-based cathodes will also be different and in a different way than the PDF NMP standard processed electrode. So this has to be adjusted to each particular cathode electrode and waterborne formulation. But I wanted to show you here with this example, and to not extend too much, this having this NMC 622 as exemplary NMC cathode active material, that also playing with different polymer binder families. All that we have screened are commercially available. You have to make sure that they are, as I mentioned, stable to up to the 4.4 or 4.5 volts versus lithium plus, just in case, because that's the potential at which the cathode may observe during cell operation, and you have to make sure that the polymer binder is stable and will not react to be able to operate as a cathode binder. But you can find, or you can screen different polymer families that could be then used and tried with NMC type cathodes. Still, in some cases, needing this pH regulator to keep the pH at around 9, not much higher than 9, which is the other key point. And also adding some additional dispersants or alternatives to the CMC, which the CMC is brittle and creates those cracking and delamination issues that I showed in some of the initial slides. So, for instance, in this case, we have tried this Panisperse, which is another type of dispersant and not a cellulosic paste. And with this formulation, for instance, has also been possible to reduce the percentage of the binder at 2%, which is already quite low, with good electrochemical performance, good rheology to go to upscaling and coating, and also to reach more than or what is now the standard of the baseline in terms of electrode loading in milliampere-hour per square centimeter. For instance, in this case, nearly 25 milligram per square centimeter per side. So thicker electrodes, but still maintaining the adhesion and the mechanical stability. So I think probably, we are past the half hour. So I can stop here. If there are further questions later on, I can show also some work with NMC 811, higher nickel content, which is additionally introducing higher degree of challenge, particularly on the leaching and the pH. But I think I can stop here, and then I hope that this has provided some insight onto this kind of cathode oxide Aqueous processing to go further on the coffee break discussion today.